Today I'm going to be talking about super resolution. You've probably seen it in multiple CSI shows where they keep enhancing images beyond all belief. So let's start off with some humor.
Enhance! Enhance!
That's not how it works in real life. You can't create information from nothing.
I can increase the contrast.
Yeah.
So that's a little hilarious because if you just said that now I can use an ESR GAN trained on rocket images, that would be quite believable. So an overview of what we'll be discussing today. What is super resolution? What are the types of super resolution? Different models that are used, what type of loss function to use, and some parting thoughts. So different types of super resolution. The main topic for today is single image super resolution, where you take one image and you pass it to a neural net and you develop an upscaled version of the low-res image. And this has many, many applications, especially taking old content, like old video content in SD and converting it to 4K, or taking images where you don't have a high resolution image available, like satellite imaging and medical imaging and surveillance, and creating a high res image of it. Then the second type is stacking multiple images to create a single enhanced image. And this is how most cell phones create images with very low noise. I have a multi-$1,000 camera that sometimes can't produce images as well as my cell phone can. This idea has been around for decades, but it's gotten much faster and easier to do. And the third type is super resolution microscopy, which is completely different. It's basically an idea of individually lighting areas to get around the 200 nanometer optical diffraction limit. So, they use some smart trickery to get around a limit that physics imposed. So I'll just briefly touch on what stacking images can do. So one of the best examples of this is the Google Pixel camera. It basically, the phone will take close to 30 images, shifting the pixels by 1 pixel over, so that is collecting red, green, blue information at each pixel. It also shifts in between pixels to get sub-pixel information to increase the resolution. It captures images at different exposures. It actually detects areas where artifacts would form due to the object moving and removes them from the stack and only takes that area from one single image. And it does all of this without using neural networks somehow. And it can process 10, 12 megapixel images a second, which is pretty impressive. And this is some example of the results they can get from a simple cell phone camera. So different types of models, and this will all relate to single image super resolution. So the traditional method is just bicubic or bilinear interpolation, which is basically you take the small image, you expand it, and then you fill in the missing pixels with pixels like neighboring pixels. And you can see it just creates a blurry image of this, like it scaled up the image, but it didn't add any information. So how do we get more information into an image? There's a concept in information theory called data processing inequality, which basically implies that processing cannot add information to the image. So if we can't get any more information from the image, the only possible way to get information is from the model itself. So a model that's trained on multiple images has a bunch of information in it, and it can use that information to enhance the image beyond anything that you could do with the image alone. So the first method of doing this was basically a neural network. And it's as simple as taking an image, downscaling it, and so you have two sets of images. You have the high-res images and you have the low-res images, and basically passing the low-res images to the model. and in a training set, and having the model compare it to the high-res images, and basically you train the model that way to basically like this low-res image equates to this high-res image. And doing that, the result improves, but just marginally. And one of the main problems with using this method is that the loss function isn't great. So what it's trying to do is basically take all, like on a pixel by pixel basis, it's basically taking the average of all the possibilities, which inherently will result in a very blurry image because it's averaging out all the different possibilities. So textures disappear. If the edge is in the wrong place, the model will be heavily penalized. So it basically blurs so that it isn't penalized for having a hard edge where there shouldn't be a hard edge. And mean square error just doesn't align with the way humans perceive images. The image over there shows a bunch of different images that have the same MSE, even though the one at the top looks much better than the one on the bottom corner. So this slide blew me away. It's basically this square, the IHR is the original, and when you downsample it, you're left with a grid pattern which has no information in it. So there is no model that can extract something out of that. So what MSE will do is just create an average. Like it doesn't know if it's a vertical or a horizontal bar, so it will just average those out. You know, what actually works better is to just randomly guess whether the bars are vertical or horizontal, because to human perception, it doesn't really matter if you get it perfectly right that the bar was vertical or horizontal. The image all the way on the right looks much better than the image in the middle, even though the information in it is wrong. So even though the information is wrong, it's the better model, and it allows you to create edges and details. Some of those details might not be accurate, but they'll be perceived to be much, much better than the MSE. So there's a bunch of better loss functions, which are based on one of the ones that I found really interesting was you take a labeled image from ImageNet, you downscale it, you upscale it using the model, and then you pass it to ResNet, and you see if it can recognize the label object. If it can recognize the object, that's considered to be a better model. So that's a quantitative way of testing how good the model is. Humans, you have humans rate different images. There's something called the structural similarity index, and perceptual loss, content loss, so VGG loss. So these are all replacements for MSE as a loss function. So next is GANs. So basically, we've discovered that we want some arbitrary information in the image. So the neural net couldn't give us all the texture details that we wanted. So we're going to use a GAN to basically iteratively add details based on what it believes that image will look like. Now, this is not going to be 100% accurate because it's taking some seed information and it's iterating through it and slowly improving until the point where it can generate a realistic image which has all the details that we would perceive to be accurate, even if some of those details are wrong. So this is just a slide for reference. This is how a GAN works. Basically, it has two neural networks that are competing against each other. And after every iteration, both the generator and the discriminator get better at their jobs. So the generator does a better job making a fake image, and the discriminator does a better job of finding the fake image. And then what it does is, for the next iteration, it tells the generator how it figured out that it was fake so that the generator can improve. So through thousands of iterations, it gets very, very good. There's even a newer version of the SRGAN. I listed out all the improvements that they made to it, but it does an even better job at creating more authentic information. One of the interesting things was it actually combines the MSE and the GAN models, because the GAN can go a little awry at times, so it will generate too many random artifacts. So the MSE can reel in some of the random details that the GAN might add. This is basically comparing some of the outputs. The HR is the original image. The bicubic is extremely blurry. And then the SRNet is the neural network. The SRGAN is the second image from the left. And then I'm not exactly sure what CRX is, but it's probably the extreme GAN. And you can see the same in the dog's eye on the bottom images. So some parting thoughts. Super resolution is really impressive in its results. It's getting very difficult to perceive the difference between the real and generated images. This is an issue because by design, SRGANs don't add realistic information. They are creating abstract details which make the image look authentic, but it doesn't have to be authentic. The data on which the model is trained is very important. So if you want a model to generate faces, ideally you train it on a number of faces. If you trained it on a dog, it wouldn't recognize human faces at all. In fact, it would try to take the human face and convert it into a dog if it had been trained on dogs. These are some of the articles and videos that I browsed in the preparation for this talk. And these are apparently my friends. They look like people, but they don't look like my friends. And with that, thank you.
All right. Thank you very much.